Welcome back to Chemist's Corner. In this lesson, we will be studying unitary rates, also known as dimensional analysis. The key concept in unitary rates is that multiplying by the number 1 does not change the value of the original number. For instance, 45.1 grams of pure sulfur times 1 is still 45.1 grams of pure sulfur. But what if the appearance of the number 1 is changed? Instead of 1, write 8 over 8. Since 8 equals 8, it's clear that 1 divided by 8 equals exactly 1. Therefore, the original value was multiplied by exactly 1, and the value is unchanged. 45.1 grams times 8 over 8 equals 45.1 grams. 8 over 8 then is a rational number, or a ratio, a rate, and it has a numerical value of exactly 1, or 1 unit. Therefore, 8 over 8 is a rational number with a value of exactly 1. It is a unitary rate. The definition of a unitary rate is simply that, a rational number that is a fraction with a value of exactly 1. But what if the number 1 changes appearances once again? Instead of 8 over 8, what if we use the definition of a kilo? 1 kilogram is defined by the metric prefix to be exactly 1,000 grams. Since 1 kilogram equals 1,000 grams, then 1 kilogram divided by 1,000 grams equals exactly 1. Multiplying by 1 does not change the value. So if 45.1 grams is multiplied by 1 kilogram divided by 1,000 grams, although the appearance changes, the value does not. 45.1 grams has exactly the same meaning as 0.0415 kilograms. Next, we will convert from the base unit of meters into the compound unit of micrometers using the unitary rate method. We will use the definition of micro to create the equality necessary to create the unitary rate. 1 micrometre is defined to be 1 times 10 to the minus 6 meters. Therefore, taking that equality and dividing by 1.0 times 10 to the minus 6 meters does not change the truth of the equality. They are still absolutely equal. More importantly, both sides of this equality now have a value of exactly 1 by definition. This is now the needed unitary rate, a ratio equal to exactly 1. If we multiply 24.6 meters by 1, that is 1 micrometre over 10 to the minus 6 meters, I have not changed the meaning. The unit meters cancels out, simplifies to a simple 1 in the same way that x over x would simplify to 1, leaving only the unit micrometers. Once again, the appearance of the number has changed, but the meaning has not. In proper scientific notation, it is now 2.46 times 10 to the 7th micrometers. This now has precisely the same meaning, precisely the same value as the original number. In our next example, we will convert centimeters to kilometers using unitary rates, both compound units. The best way to perform a conversion from one compound unit to another is to convert to the base unit, meters, first, and then from the base unit to the other compound unit in the second step. 2 steps will require 2 different unitary rates, that is, 2 values of 1. First, set up the necessary equalities to convert from centimeters to meters, and from meters to kilometers using the definitions of centi, 10 to the minus 2, and kilo, 10 to the positive 3. 1 centimeter equals 1 times 10 to the minus 2 meters. Divide both sides of this equality by 1 centimeter to place the unit centimeters on the bottom. 1 kilometer equals 1 times 10 to the 3 meters. Divide this equality by 1 times 10 to the 3 meters to create a unitary rate. These 2 unitary rates can now be substituted into our original equation first converting centimeters to meters with our first unitary rate, and then converting from meters into kilometers using our second unitary rate. Note that centimeters cancels, meters cancels, and the only unit left is the unit kilometers, which was, of course, our ultimate goal. In both cases, the 13.5 centimeters was multiplied by exactly 1. Therefore, the value of this original number is unchanged. It has the same meaning as before. In proper scientific notation, 13.5 centimeters is exactly the same as 1.35 times 10 to the minus 4 kilometers. It has the same value. In our third example, we will convert hours into seconds. Using time units instead of distance units, again, will require 2 steps, 2 different unitary rates. First, converting hours into minutes. Second, converting minutes into seconds. Of course, the equalities, 1 hour equals 60 minutes, 1 minute equals 60 seconds. In the first case, we will divide both sides of the equation by 1 hour to create a unitary rate. 60 minutes over 1 hour equal to exactly 1. And in the second case, we will divide by 1 minute to create the unitary rate of 60 seconds over 1 minute, equaling exactly 1. 2.6 hours is multiplied by 60 minutes over 1 hour to cancel the units of hours. At this point, we have minutes. Next, we will multiply by the second unitary rate of 60 seconds over 1 minute to cancel the units of minutes. This leaves us with seconds, which was again the ultimate goal. The mathematics will simply be 2.6 times 60 times 60, but in both cases, the 2.6 hours was multiplied by exactly 1. The answer presented in proper scientific notation then becomes 9.36 times 10 to the 3 seconds. That is 9,360 seconds. However, the original number only had 2 significant figures, so in the correct number of significant figures, 9.4 times 10 to the 3 seconds. That now has exactly the same value as 2.6 hours. When working with derived units, such as areas or volumes, the initial process is the same, but there is one additional third step. As before, set up an equality as defined by the metric prefixes. Then divide both sides of this equality by the unit that you wish to cancel out, usually the unit that you started with. The third step is, if it's an area, square both sides of the equality. If it's a volume, cube both sides of the equality. As long as you're doing it to both sides, it is still equal. It is still a unitary rate. You can still multiply your original number by this unitary rate without changing its value. For instance, if we are converting 5.7 square meters into square millimeters, we start with the equality 1 millimeter equals 1 times 10 to the minus 3 meters. Create the unitary rate by dividing both sides of the equation by 1 times 10 to the minus 3 meters. Now square both sides of the equation. 1 millimeter simply becomes 1 millimeter squared. However, the 1 times 10 to the minus 3 meters becomes 1 times 10 to the minus 6 square meters. The unitary rate then is now 1 square millimeter on the top, 1 times 10 to the minus 6 square meters on the bottom. Multiply by this 1. This will cancel out the unit square meters and give you 5.7 millimeters squared divided by 10 to the minus 6. Bringing the exponent to the numerator gives you an answer of 5.7 times 10 to the 6th square meters. That is how many square millimeters there are in 5.7 square meters. Our fifth example also deals with a derived unit, but not a derived unit of volume or area, but rather a derived unit made from distance divided by time, that is, a speed or perhaps a velocity. In this case, we're converting 50 kilometers per hour into meters per second using unitary rates. Both starting and ending units are derived from two different measurements, distance and time. Therefore, each unit should be treated independently. The order of these conversions is actually not important at all, just that you do both of them. The key to success is setting up the original value. Rather than writing as 50 kilometers/hours, consider the meaning. In 1 hour, the distance traveled is 50 kilometers. Therefore, write the original number as 50 kilometers divided by 1 hour. We will then multiply this by a pair of unitary rates, one to convert the distance unit and the second to convert the time unit. Write the true statements. 1 kilometer is 1 times 10 to the 3 meters. 1 hour is 3,600 seconds. In this case, we want to cancel out the unit kilometers, so divide both sides of that equality by 1 kilometer. The unitary rate will then be 1 times 10 to the third meters divided by 1 kilometer. For a second unitary rate, we already have hours on the bottom, so we want to put hours on the top to cancel it out. Therefore, divide the second unitary rate, or rather the second equality, by 3,600 seconds to create the second unitary rate, which will now be 1 hour on the numerator divided by 3,600 seconds in the denominator. Simply substitute in the ones in our original formula with our two unitary rates. Kilometers will be cancelled and leaving meters. Hours will be cancelled, leaving seconds. The final answer then will have a unit of meters per second. So 50 times 10 to the third divided by 3,600. That works out to be 13.89 meters per second. However, to two significant figures, it would be rounded to 14 meters per second. When using the unitary rate method, converting from any base unit to a compound unit will take exactly one step. From any compound unit to the base unit, again, it will take only one step. However, when converting from a compound unit to a second compound unit, at least 2 steps will be recommended, perhaps more. With the unitary rate method are key steps in the process. Number 1, set up an equality based on definitions, metric definitions, the mole calculations, etc. Divide both sides of the equality by the same quantity. That is the quantity with the unit you're trying to get rid of. Multiply the original number, that original value, by the 1, the unitary rate, that was just formed by the division. And remember, at the end of the day, the values have not changed. Only the appearance of the number has. If you enjoyed this video on unitary rates, please hit the like button, leave a comment below, and subscribe to my channel. Chemist Corner loves new people. If you're looking for videos that actually use unitary rates, check out my atomic mass and molecular weight, what is the mole, 6 types of mole calculations, and molarity calculations. All of them utilize the unitary rate method. See you soon in Chemist Corner.